Yes. No, video is finished.
Sorry?
You can turn on the videos.
Turn on the, okay, sure. Okay, great. Hello, everyone. It's great to be here. I'm Biwei Huang from UC San Diego. So yeah, it's nice to be here and thanks for having me. So today my presentation will be enhancing reinforcement learning, especially to mitigate the issues like the data scarcity, the lack of interpretability, and the generalization issues in reinforcement learning from a causal perspective by leveraging causal representations and graph structures. So although we know, like with large models, we can solve the generalization problem to some extent. So here I will mainly focus on small models and how to incorporate causal constraints, causal understanding in large models will also be another topic to explore. Okay, let's first see some preliminaries in reinforcement learning. Let me move this to somewhere else. Okay. Hide, maybe hide.
This one.
Okay, cool. Thank you. Okay, so we all know that reinforcement learning aims to learn policies that maximize a reward function by interacting with our world. And typically, it is formulated as a Markov decision process. And here's a graphical illustration of the Markov decision process. Now we can see we have the states as the action A and the reward R, as well as the cumulative reward, the capital R. So, and here we also use the ages to represent the causal relationships among different variables. For instance, the causal relationships from ST-1 to ST, and the causal relationships from A to S, and also the causal relationships from ST to RT. And also, would like to emphasize that you can see here, AT-1 may not influence every state. And similarly, the reward R may not be influenced by every dimension of the state. Okay, so later I will emphasize more on this point. So here I would like to give you an intuition that we can model the reinforcement learning with MDP, and at the same time we can use a graph to visualize the MDP and visualize the underlying causal process. And moreover, we know that in practice, we may not directly observe the states, the underlying states, but instead, for example, observe the image pixels. And in this case, we can formulate it as a PUM-DP problem or block MDP problem. For instance, here, the O variables represents the observed image sequences. And the states and the underlying dynamics are latent. So here, we need to learn the underlying latent states and dynamics from the observed high dimensional image pixels. Okay, so we know that in current years, we have seen so many successes in reinforcement learning. However, some issues still remaining. For example, lack of interpretability and not generalized so well. So the current most current IR algorithms cannot generalize very well to a very new task or to a very new environment, even with subtle changes. and it may need a lot of data, much more than our human experts needs. But we know that in many tasks, we cannot obtain so much data. And at the same time, it may lack interpretability. And many algorithms, for instance, many algorithms may directly input the image pixels and learn a policy function in a way of black box without really understanding which states are essential for policy learning and which states are controllable. And also this kinds of way makes generalization very hard. For example, if we have already learned the policy very well in a simulated environment, then how can we extend it to a real-world environment? How can agents quickly learn to drive in a real-world environment, which is much more complex than the simulated environment? So here, in the following, I will show how can we mitigate such issues from a causal perspective. So basically, if we can understand the underlying causal process, whether we can make the reinforcement learning model generalize better and needs fewer data and has better interpretability. Okay, so basically, I will introduce two types of works to show how can we enhance reinforcement learning through causal presentations and graph structures. The first work will be on learning word models with identifiable factorization. And furthermore, I will show how can we do generalization in RL by understanding what, where, and how to adapt from a causal perspective. Okay, let's see scenario 1, learning essential features for policy learning action control. Okay, let's first imagine the following scenario. So an agent is driving a car on the street. Now, which information the agent receives? For instance, the agent may receive the information about the speed, position, and the direction of the car. And it may also receive like the information from the surrounding vehicles, how the other cars are driving. And also, it may receive information about music and air conditioner, as well as some remote sceneries. Now, how can the agent know which information is essential for the agent to control the car and to achieve the reward? For example, to arrive the destination as soon as possible, and which parts is controllable. So basically, based on whether the information is reward relevant, that is, which is useful for policy learning, and which information is action controllable, we can divide the underlying states into 4 categories. So basically, the first category, like the speed, position, and the direction, they are both reward relevant and controllable. So we denote it by SAR. A represents action and R represents reward. And the second type of information, like surrounding vehicles, they are reward relevant because the other cars will also affect my driving. But however, it is uncontrollable. So the agent itself cannot directly control other cars. So we denote this type of state by SA bar R. So means not controllable, but is reward relevant. And the third type of information is reward irrelevant, but action controllable. For example, the music and the air conditioner. We denote it by SAR bar. And the last information is just noise, which is either reward irrelevant and uncontrollable, such as remote sceneries. And here's a graphical illustration of these 4 states. And here, of course, in most cases, we only observe the image sequences, and the underlying states are latent. Okay, and interestingly, you can see, let's see the graph structure of this MDP. You can see for for SAR and SA bar R, you can see they have a direct edge or a path to the reward signal RT. For instance, here, SAR has a direct edge to RT. And also for SA bar R, it has an indirect path to RT. But anyway, it has an influence to the reward. And for other states like SAR bar, the signal 1, and the SAR, they are directly controlled by the action A. So basically, you can see each different type of states have different causal connections to the other variables. Okay. Now the question is, how can we learn the latent states to distinguish the different categories of the states and identify the underlying dynamics? So, and we also see the differences in the graph structures for the different categories of states. Now the problem is, how can we identify them? So basically, we want to find a connection between the graph structure and statistical independence. So if we can build a connection between the graph structure and statistical independence, then we can make use of such statistical independence or dependence from the data to recover or to distinguish between the 4 different categories of states. So specifically, if a latent state SI is reward relevant, if and only if it is dependent on the cumulative reward, capital R, given the previous action and the state. And moreover, if a state is action controllable, if and only if it is dependent on AT-1 given previous states. So we make use of such connection between the graph structure and statistical dependence to recover the different categories of latent states. And during the implementation, to ensure, for example, to ensure SR is minimally sufficient for policy learning. So we maximize the difference between these 2 kinds of mutual information. So basically, we want to maximize the mutual information between SR and the capital R, given the previous actions and the rewards, and while minimize the mutual information between SR bar and the capital R, given previous information. And similarly, to ensure SA is directly controllable and contains minimal but sufficient information for controllability. So we maximize the mutual information between SA and A-1, AT-1 given the previous state, while minimize the mutual information between SA bar and AT-1 given the previous states. So, okay, now let me show you the main identifiability condition. So we know we only observe the image sequence and we want to identify the latent states. Now we want to know under which conditions the underlying latent states are uniquely identified. So basically, we need to make use of following condition. So let's suppose we have a function f from the latent states and some other signals. Let's use eta to represent it to the observed pixel space OT and the reward RT. And if the mapping F is smooth and invertible with smooth inverse, then generally we can recover the latent states up to some trivial indeterminacy. Okay, so this is the theoretical identifiability condition. Now, given the theoretical condition, then how can we estimate the model and perform the policy learning? Basically, we do model estimation and policy learning in the framework of Dreamer. It contains 3 main components. The first component is word model learning. So we need to collect some data, and then we need to learn the word model. That is, we need to learn the observation function from the latent states to the observed pixels, the latent dynamics of the states, as well as the reward function. And furthermore, with the learned world model, now we can do policy learning by imagination or say by dreaming. So we can imagine trajectories given the estimated world model, and then we can update the policy directly without interacting with the real environment, but only based on imagination, since we already understand the underlying state dynamics and the reward function. And furthermore, after some iterations, we also interact with the environment to update the data sequences, and then iterate these three components until convergency. So now you can see the good point, a very important point, and very important point here is that if we can learn the world model very well, then we don't need to interact so much with the environment. We can imagine, but instead we can do imagination. We can imagine what would be the next state if we had taken this action. So we like we can understand the counterfactual question. Okay, here are some experimental results on latent states recovery. So here we use R-square to show whether the latent states are the recovery of the latent states are good. So basically, R-square means coefficients of determination, and here we use kernel ridge regression to regress the estimated latent states on the true latents, and also regress the true latents on the estimated latents. So if there's a one-to-one mapping between the estimated latent states and the true latent states, then the diagonal part of R-square should be 1. And you can see we got very good results. The diagonal entries are almost 1, and the off-diagonal entries are mostly close to 0. And these two figures shows the R-square value, with the training steps. And this is our approach, the blue one, which can converge quickly to 1 compared to other baselines. And also, we also modify the catapult, the traditional catapult with 2 distractors. Okay, let's see this first line. So basically, we include another catapult, and for the first row of the catapult, it is not reward relevant. This is the first distractor, and the second distractor is the green bar on the second row. So this green bar is action controllable, but it is not reward relevant. And we want to show whether we can really identify which components is policy reward relevant, which component is like reward irrelevant and action controllable, and so on. And for instance, we find that the cut position in the second row is action controllable and reward relevant. And for the pole angle on the second row, it is reward relevant, but not action controllable, because we know in catapult, the force is directly added on the cart to control the pole, right? And also we find this green bar is action controllable, but not reward relevant. And moreover, the distractor in the first row, basically the first catapult, is neither action controllable nor reward relevant. Okay, here's the experimental results on policy learning. And this blue line is so basically it is minimal sufficient for policy learning. And we find without surprise that it achieves the best performance. And let's also see the red line, which uses all the states. And you can see the red line the performance of red line is a little bit worse. And also more interestingly, you can see the purple line, which is reward irrelevant, so SAR bar. And then you can see it cannot learn the policy at all. Okay, now let's see another scenario. So we know in real world environments, so the environment is always changing. Now, how can we use causality to guide the adaptation and the generalization so that we can adapt the policy learning as efficient as possible? So first, let's see why causality could help. So here I list several advantages of why causal understanding could help. For instance, with the causal understanding, we can identify the underlying world model, or typically we often call it environment model. So basically, the underlying causal process. And furthermore, we can localize what and where the changes are. So in practice, we often see the change of distribution of a large number of variables, but usually the changes are localized. So if we can identify or pinpoint what and where the changes are, then we only need to adapt the corresponding component. And in many cases, it could maybe only a few components are changing. And furthermore, so some changes may not lead to the change of policy. So with a good understanding of the causal process, we can identify a minimal sufficient set of factors which are essential for policy transferring, instead of consider some non-essential changes. And furthermore, we can understand how the factors are changing by understanding the underlying causal process. For instance, in the very simple catapult game, if we move the system from the Earth to the Mars, so basically, if the agent can know only the gravity changes, and the gravity can use a one-dimensional variable to represent, then it can adapt to the new environment on Mars very quickly. Or maybe only need a few samples to update the estimation of the gravity. Okay, and here's a more complex scenario. For instance, when you play the game, so you have already been well trained on level 1. Now, when you go to level 2, how can you make use of the previous knowledge and quickly adapt to level 2? Besides distribution shifts, level 2 may have additional new variables and additional actions. Then how can you quickly adapt to a more complicated level? Okay, now let's first model the world environment model with explicitly structured constraints. So basically, the environment model contains three components: the state dynamics, the reward function, and the observational function. And here's the graphical illustration. So we observe the image sequences O, the action sequence A, and the reward sequence R. And moreover, we make use of the D matrix to encode the structure relations among those different variables. And here, D is a binary matrix, and it is a free parameter that we need to estimate from the observations. So you can see, so basically D encoded the causal relationships among different states, the causal relationships from S to O, from S to R, and from A to S. Okay, here's some results on the next state prediction error with and without considering the structure constraints. So we can see these three approaches consider structure, but with different strategies to learn the structure. And you can see for those that consider the structure, they usually have a lower prediction error for the next state, especially for this blue line. And this is the results on policy learning. And again, we compare the approaches with and without structure constraints. And here, the higher the beta. And we can see this blue line, the red line, and the purple line, which consider the structures, usually have a beta. We usually have a beta performance in policy learning. And of course, different ways to learn the structure also matters a lot. Okay, now let's consider how can we make use of causal understanding to pinpoint what will and how to adapt and generalize in a simple case with distribution shifts. Let's imagine the following scenario. Suppose we have multiple domains. And in each domain, there could be distribution shifts and also the changes in the transition dynamics. For instance, if we move the system from the Earth to the Mars, then the gravity changes. And also we can add some corrupted noise on the observed image space. Now, how can we, besides the structure relationships, how can we model the changes in the distribution shifts? Model the distribution shifts. We know traditionally, we may need to model the whole environment in a new domain. So we basically in a new domain, we need to retrain the dynamics model, the observation function, and the reward function with a lot of data, because it may need a lot of data. Now, instead of model everything from scratch in a new domain, we use a compact representation to model the environment shifts or model the distribution shifts. So here we use a low dimensional vector theta to characterize the distribution shifts. So specifically here, theta S. So theta S model the changes in the transition dynamics. And the theta O models the changes in the observation function. And the theta R models the changes in the reward function. For instance, in the example I give, so when you move the system from the Earth to the Mars, only the gravity changes, right? So we only need to use one dimension of theta S to learn the change of the gravity. So basically now in a new domain, you only need a few samples to update this one-dimensional theta S. And of course, so here we only observe O, the image sequence, but without observing the latent states S as well as the change theta. Okay, so we can see with this graphical representation, we can have a compact way to encode what and where the changes are. And then let's see this graph. So you can see not all state dimensions are necessary for action prediction. From this graphical illustration, only S2 and S3 are essential for policy learning to maximize the reward. This is because only S2 and S3 influence the reward, but not S1. So which means that in reward in policy learning, we don't need to take into account S1. And furthermore, not all the theta are necessary for adaptation. So basically, we use theta to encode the changes, encode the distribution shifts. And here we have theta O and we have theta S. Theta O is to characterize the changes in the reward function, in the observation function, and theta S is to characterize the changes in the transition dynamics of different state dimensions, as well as theta R to capture the changes in the reward function. So here, we only need to, for example, in this example, we only need to take into account theta s. For instance, the gravity change when we move the agent from Earth to the Mars. We only need to consider the change of gravity, which is captured by theta s. And of course, we also need to take into account theta r, which is used to model the change of the reward function. And moreover, another good property of the causal system is that thanks to the modularity of the causal system, each factor can be adapted separately, so which avoids like the curse of dimensionality. So you can see by explicitly considering the structure constraints and model the changes in a compact way, we can achieve more efficient, interpretable, and effective adaptation. So we can know what and where are the changes and pinpoint which changes are essential for policy adaptation. Oh, 2 minutes? Okay. So here's an experiment on the Atari Pong game. So we change for example, we make several changes on the environment, like change the orientation, change the size, change the color, change the noise level, and so on. And we compare our algorithm with others like propagation neural network, and we can see our methods achieve a good performance with very few samples. Okay, now let's see a more complicated scenario. So for example, when you, how can you adapt from a easy game to a more complex game? And for also, how can you adapt to your skills from driving in a simulated environment to driving in a real world environment, which may involve some new state variables as well as action variables besides the trivial distribution shifts. Okay, so in this case, how can we make use of causal understanding to do adaptation and generalization when there are state action space expansion? So basically, I summarize the 3 crucial points. The first point is that how can we characterize the distribution shifts? So basically, as you have seen, we use a compact representation to embed the changes in the transition observation and the reward function. Then we can automatically learn what and where are the changes are in the current variables. And also we can learn the changes, basically learn the distribution shifts in a very efficient way, since the changes are embedded in a very low dimensional vector. And furthermore, how can we characterize the state action space expansion? So basically, we can add new variables to the current system with self-adaptive RL strategy. So if you find that the first strategy is not enough for policy learning and for word model learning and for policy learning, then we will consider to add new variables to the current system with an automatical procedure. And furthermore, let's see the benefits of explicit causal structure. So if we consider the structure explicitly, then we can prune the causal graph very easily. Right, we can temporarily disregard variables which are irrelevant to the current task. And furthermore, we can reuse those variables when necessary. We didn't like directly through them, but like we may put it somewhere and we can directly use them when necessary. And furthermore, with this structure, explicit structure, then we can preserve previously acquired information. And also we can customize the minimal sufficient state variables for each task. Basically, with this strategy, I would like to claim we can solve the catastrophe forgetting problems in continual learning in most cases, because we don't need to relearn everything and like forget the previously learned information. Instead, we use some like very low dimensional variables to characterize the changes explicitly. And with the structure, we can reuse them or like temporarily disregard them in the current task. This is a diagram. So basically, so for instance, if you have learned the what model and learn the policy in the current task, now you want to generalize it to a new task, then you first update the task specific data. And if you find the prediction and policy learning is very well with this strategy, then you can just use this strategy. But otherwise, if you find it's not enough, okay, then we may need to add new state variables and action variables. And yes, and furthermore, we because of the explicit graph structure we use, then it's very easy to like prune the current pruning the current state and also reuse the state in a very easy and efficient way. Here are some results. So basically, the first figure is the original task, the cumulative reward in the original task. And the second figure is in the case with distribution shifts. And the third figure is that there are new state variables. And furthermore, we consider another task is that there are both distribution shifts and the new state space. Okay, and with our strategy, you can see the red curve. They can adapt to different scenarios very well compared to others. And this is the generalizing performance in the Atari games. And basically with different mode and with different difficulty level. And basically the red curve is our methods. Okay, let me make a quick summary. So we can see with causality, reinforcement learning can achieve interpretable, efficient, effective, and more generalizable RL by understanding the underlying causal process. The essential point is that we aim to understand the underlying causal process. And then by understanding the underlying causal process, we can disentangle different categories of state variables to see which variables are essential for policy learning, which variables are action controllable. And with causal understanding, we can identify what will and how the changes are in adaptation and generalization, instead of doing everything in black box. And also another point I didn't mention is that we can also use, by understanding the causal process, then we can do counterfactual data augmentation to address the data hungry problem in RL. Yeah, but of course, causality is one essential point we can leverage in the RL system. And of course, there are many other properties we can make use of in order to make reinforcement learning really work in practical problems. Okay, thank you so much.
All right, to our speaker. We'll have to go straight to the contributor talks just because there's just because of time. But for contributor talks, if you can